This video covers gravity. Now you've seen this equation before. This is a force of gravity is equal to capital G, which is our gravitational constant, 6.67 times 10 to the negative 11, times m1 times m2 over r squared, where r is the distance between the center of mass of the two objects. It's the distance between center of masses. Now this picture shows that normally when you're dealing with satellites or things orbiting, you will not necessarily be given the center of mass of the satellite, but you will be given the center of mass of the Earth. So you're just going to assume that the satellite is a point mass and everything else is going to work as is. Now here it's really important to understand that the force exerted on one is equal to the force exerted by the other. This F1 and these F2 are equal in magnitude but opposite in direction. Again, this follows Newton's third law. It's very common to see these types of questions on the multiple choice section of the AP exam to tell you what happens if one of the masses increases. What happens to the force on the other mass? Well, that increase is going to affect both of them equally. Now, if I ask you to solve for the gravitational force, or weight, you would tell me mg. Well, our own gravity, 9.8, comes from this equation, g, m1, m2 over r squared. So here you can see that one of the masses will cancel out. This is usually the mass of the object. And what's left is g m over r squared, where m is going to represent the mass of the planet, in this case Earth. Now this equation gives you the gravitational field strength at a certain point. Again, you can see this is very similar to our electric field strength, kq over r squared, where it's just dependent on a charge. Well, here we're dependent on that giant mass, in this case the Earth. Again, this equation tells you the gravitational field strength. On your AP sheet, you're actually going to be given this version of the equation, where you're going to have a negative sign included and an r hat. What this r hat means is this unit vector, which tells you the direction the force is going. Again, it's probably better for you to just use the equation we wrote earlier, g times m1 times m2 over r squared, to find the magnitude of it, and then find the direction through your own conceptual understanding. Again, we aren't going to be using this negative later because this negative means that it produces a bound orbit. And we'll see an example of simple harmonic motion where we needed that restoring force, but we'll see that a little bit later. In this example, it says how far from the Earth's surface must an astronaut in space be if she is to feel gravitational acceleration that is half what she would feel on Earth's surface. Now, you might think this is a straight plug and chug, but we need to remember that our gravitational field, or gravitational acceleration, is just g times the mass of the planet, in this case Earth, divided by r squared. Now r is the distance between the two center of masses. So when we are looking for the distance away from the Earth's surface, that means we have to include the radius of the Earth plus the distance that she is going to be away from the surface. Those two distances together make up the total distance. So this would be RE. And if she's over here, this would be the additional R. So in total, this would be the total distance between the center of mass of the two objects. Again, you want to solve for this little r. So that means we need to rearrange the whole thing. So we can bring little g down to the bottom. RE plus R squared up to the top. Square root. And then we want to solve for little r so we can subtract. So the distance that she needs to be away from the Earth's surface is the square root of g times capital M over little g minus RE. If you plug in all of your numbers, again for capital G, we have 6.67 times 10 to the negative 11. For capital M, again, that's the mass of the Earth. These are going to be constants you're going to be given if you need to use them or actually calculate something. They're going to be found on your equation sheet. Little g, again, we want to know when she would feel half of what she would feel on Earth. So if on Earth it's 9.8, we would want her to experience 4.9. And then again, the radius of the Earth is 6.37. All of this information can be found from your equation sheet. If you put all that into your calculator, you should get 2.64 times 10 to the 6th meters. This is the distance away from the Earth's surface, not total distance away, but the distance away from the Earth's surface she needs to be in order to feel half of the gravitational acceleration she would feel on Earth. So let's look at this equation again. We know that as r decreases, our force of gravity is going to increase. But let's say that you dig a hole through the center of the Earth. Now, this is actually a very common AP problem. So when you jump down and are at a radius r from the center, the portion of the Earth that lies outside a sphere of radius r does not produce a net gravitational force on you. That means that the portion that lies inside of the sphere does. This implies that as you fall, the sphere changes in volume, mass, and density due to different types of rocks. This also tells us that your weight, again your force of gravity, actually decreases as you approach the center of Earth from within the inside of the sphere, and that it behaves like Hooke's law. You will oscillate. Again, the density of the planet depends on the mass over volume. So in this case, the volume of a sphere will be 4/3 pi r cubed. So if we're trying to determine how much of the mass is actually depending how much force of gravity we experience, then we can say that our density times 4/3 pi r squared cubed, equals the mass that's affecting us. So as r starts to decrease, so will the mass that affects us. So let's use that information and plug it into our force of gravity equation. I'm going to use capital M for the mass of the planet, little m for the mass of the person, or the object. Again, capital M is going to be replaced with rho, 4/3 pi r cubed. And this simplifies down to g times rho, 4/3 pi m times r. Now, all of this inside of parentheses are going to be constant. The only thing that's actually changing is this r. So we can replace this entire thing inside the parentheses with a k to represent a constant. Again, we can see how this relationship is very similar to Hooke's law. Remember that in simple harmonic motion, we saw that this particular equation created simple harmonic motion, meaning that you are going to oscillate. Again, going back to the fact that you will oscillate as you go through the center of the Earth. So let's try this example. It says a 150 kilogram astronaut now stands at the bottom of a hole that is 1.6 times 10 to the 6th meters deep. The radius of the planet is 3 times 10 to the 6th meters. Assume that the planet's density is uniform and our rho is equal to 7 grams per centimeters cubed. We're asked to find the force of gravity on the astronaut. Again, as you go to the center of the Earth, the force of gravity, or the mass that affects your force of gravity, is going to start to decrease. Again, it's going to depend on the density of the Earth, which is the mass divided by its volume. So to determine the mass that affects your force of gravity, it would be density times volume, or density times 4/3 pi r cubed. Again, we can plug that in for the mass of the planet. That'll be rho, 4/3 pi r cubed. Same derivation. Again, being able to go through the entire process is going to be important. Times the mass of the astronaut over r squared. the distance from the center of mass to where the astronaut will be. Again, these r's will cancel out, and you're left with one r on top. And you're left with g times rho, 4/3, pi r m. Now, the last thing you need to do before plugging in your numbers is solving for rho. We're given rho, but it's in grams per centimeters cubed, and we know that we have to work in kilograms and meters. So if we have 7 grams per centimeter cubed, we can convert that to 1,000 grams per kilogram. And because the centimeters cubed is cubed, we need to do 100 centimeters per meter 3 times. So that our rho is now 7,000 kilograms per meters cubed. So now we can plug in all of our numbers. Again, g is 6.67 times 10 to the negative 11. Rho is now 7,000. 4/3 pi. The distance from where the center of mass is to where we are is 1.6 times 10 to the 6th. And then the mass of the astronaut was 150 kilograms. 469.4 newtons is our force of gravity acting on the astronaut. In this example, a hole is dug all the way to the other side of the planet. The astronaut jumps in the hole, and we're asked to describe the astronaut's motion. Again, we said based on the equation that we're going to have simple harmonic motion, and we're going to oscillate about the center. Here we're asked to find the force of gravity on the astronaut at any position r, and the time it takes to complete one oscillation. Again, this is a force of gravity equation that we just derived. Remember that force of gravity is equal to mass times acceleration. In this case, we can write acceleration to be the derivative of position with respect to time. Second derivative of position with respect to time. Again, this is a review of the simple harmonic equations that we derived earlier. So, we can replace r and the second derivative with a function that we know the solution to. Again, in previous examples, we've used x is equal to a cosine theta, or omega t. Here we can just replace it with r because r is just representing position anyway. We can make this substitution and say that this whole mess times a cosine omega t equals our second derivative of this equation. Again, I'm going to cancel out my m's here, so that could have gone out. And we're left with negative omega squared a cosine omega t. If you don't remember any of this, you should definitely go back and review the simple harmonic motion video. Again, a cosine cancels out with a cosine, and we're left with negative g 4/3 pi rho. Again, our mass is canceled out. Here, these negatives can cancel out, and we're left with, again, this is very similar to equations that we've seen before when we've derived our period. Remember that if I take the square root of both sides, omega is equal to 2 pi over t. Well, t is the period, the time it takes to complete one oscillation, and that's what we're trying to solve for. So t is equal to 2 pi. If a fraction goes down to the bottom, we can just multiply by the inverse. So this is 3 over g 4 pi times rho. This is the time it takes to complete one cycle. If you plug in all of your numbers, you should get a period of 4,492.9 seconds, which is about 75 minutes. Now we're going to go over a few other things you need to know. These are energy considerations. Now remember from mechanics that work was equal to the integral of F dot dr. Well, in this case, our force is G m1 m2 over r squared. We want to take the integral of that from a distance r to infinity. Well, G, m1, and m2 are all constant, so we can pull those out of our equation. And all we're left with is 1 over r squared dr, or just r to the negative 2. When we take the integral of that, we get negative 1 over negative 1. Again, we still have those constants. And we need to evaluate it from r to infinity, which just becomes negative 1 over infinity minus a negative 1 over r. Now, we are missing a negative here. Remember that our equation actually includes that negative. And at the very end, we get that work is equal to a negative G m1 over m2 over r. Now, this negative sign should not surprise you, as we already know that work was equal to the negative change in U, or mgh, in this case, potential energy. So that means that G m1 m2 over r gives us potential energy. So our equation again gives us gravitational potential energy. The gravitational potential energy near a planet is negative, since gravity does positive work as a mass approaches. Again, this negative potential is indicative of a bound state. Once a mass is near a large body, it is trapped until something can provide enough energy to allow it to escape. Which brings us to escape speed, which means that our potential energy will be equal to our kinetic energy at our maximums. Again, we know that energy will never change. As the rocket leaves the Earth, its kinetic energy is large and its potential is small. As it ascends, there's a transfer of energy such that the difference between the kinetic and potential will always equal 0. So, if we set our gravitational potential energy, maximum, equal to 1/2 mv squared, then what we get is our escape speed. Again, this equation is just rearranged. Again, this is probably one of the most common applications of our gravitational equation, so make sure you include it in your notes. And the last thing is Kepler's laws. Now, they are all in orange because it's very important that you know these definitions. Now, these are the 3 laws that Johannes Kepler formulated when he was studying the heavens. The law of orbits, which means that all planets move in elliptical orbits, with the sun at one focus. The law of areas, a line that connects the planet to the sun sweeps out equal areas in the plane of the planet's orbit in an equal time. That is, the rate of our change in area over change in time at which it sweeps out area A is constant. And the law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit, and we'll see examples of all 3. Again, in this picture, we have the major axis labeled and the minor axis labeled, with the star at one focus. Again, all planets move in elliptical orbits unless the problem specifically says that it's moving in a circular orbit. Again, this picture kind of shows a really good example of the star at one focus. Also, Kepler's second law says that stars sweep out equal area in equal time. So this second picture shows that the area that it sweeps out here is same as the area swept out here, and the amount of time it took to sweep out that area is the same in both situations as well. Now, the most important part is this piece down here, that the star and planet both orbit around this center of mass. So if you're asked to draw the orbit, like in the first example problem given in the assignment, you need to solve for the center of mass, and that's going to be about the point where they orbit. And we'll see an example of that later. And the last one, Kepler's third law, the law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis. What that means is if you start off with our gravitational force, and we know that this gravitational force is what keeps objects in orbit, meaning that it provides a centripetal force, then we can see that one of the masses will cancel out, and we're left with capital M, which is the mass of the planet. And again, one of these R's will cancel out. So remember that if it's moving in a circular orbit, that velocity was 2 pi r over t. Again, we're pulling a lot of stuff from mechanics back. So this piece becomes squared, and we get 4 pi squared r squared over t. And if we rearrange and solve for t squared, we get t squared equals 4 pi r squared, 4 pi squared. We're going to have r cubed over g times m. Now you can see that everything inside that I've circled is a constant, so my period only depends on the distance. Now again, this derivation is going to be important to be able to recreate. So one last thing about energy. Using our orbital speed derived from the Kepler's third law and the formula for kinetic energy, we can define the kinetic energy of an object in a bit more detail when it is in orbit around a body, which means it can be rewritten as 1/2 m times g times m over r. Again, if you look at this equation, this is just half of the potential energy equation. Now, the reason that this equation is so important is because this greatly simplifies the math. If we use regular kinetic energy along with potential, we will need both the orbital velocity and the orbital radius. In this case, we only need the orbital radius. So if we want to solve for the total energy, we wouldn't even have to use velocities. We can just use the equation that we just derived, which is this portion right here, plus our potential energy equation, which would give us negative g times m times capital M over 2r. And finally, as the radius of motion gets larger, the orbiting body's kinetic energy must decrease. Again, we know that if we throw an object up, its kinetic energy is going to slow down, but its potential energy will increase. So, as it slows down, its potential energy is going to increase, therefore become less negative. So by saying become less negative means that we have to find our zero position for our potential energy at infinity.